All right, everyone. So we are taking a quiz today on our roller coaster problem. We did this worksheet last class. We presented on it. So you should have been able to do your corrections in class that day. And then, of course, if you had any trouble understanding the concepts, you would go home and look at the video answer key or the regular answer key and get understanding on that. The focus of this quiz is on gravitational potential energy to kinetic energy and back to gravitational potential energy. So I didn't put this on the warm-up, but I do want you to do an LOL chart of this scenario, and that'll help you get started on how to solve these problems. And you are going to have an LOL chart on your quiz. So conservation of energy and gravitational and kinetic energy. So in your homework, the concept builder, it talked about potential energy. We have two types of potential energy, but for this problem specifically, we don't have elastic potential energy because there's no spring, there's no sort of rubber-like contraption. So it's gravitational potential energy you're focused on. And obviously, you want to know those equations, at least know where to find them in your physics helper and how to use them. And then the concept of conservation of energy. Energy is never lost, only transfer to different forms. I will show you a different way to calculate these also. Obviously, you'll get the same answer, but it'll be really helpful for today's worksheet. So today's worksheet, we're going to do exactly what we did here, except we're going to focus on different energy types, not just gravitational, not just kinetic, but just a combination of all of them, all our mechanical energy types anyway. But for this one, we're going from gravitational all the way to kinetic, conservation of energy, meaning 4 blocks need to equal 4 blocks. And one thing I want to highlight is we've got the cart and a frictionless ramp. And we need one more thing in this system to make our gravitational potential energy be a valid energy type. Can anyone tell me what that is? Lindsay. We need Earth. Earth is what creates gravity. Without gravity, we wouldn't have a gravitational potential energy to pull it down. So you want to make sure to include Earth. The same way you want to make sure you include a spring or a rubber elastic or whatever creates the elasticity if you had elastic potential energy. So let's go on to any questions on the LOL chart. First of all, that's our foundation. Let's go into the problem solving. So here we are told that the height of our cart is 5. We're told the mass is 40, and obviously we've got our 9.8. This is our equation for gravitational potential energy. You want to make sure you know how to use it. You want to know where it is in your physics helper. And so you're going to plug in your 40 kilograms times 9.8 meters per second squared times 5 meters, and then you get 1,960 joules. So because of conservation of energy, you're going to set that equal to your kinetic energy equation, which is 1/2 mass times velocity squared. You're going to plug in your 40 for the mass, divide 20 to both sides because half of 40 is 20, and you get 98 equals v squared. Of course, to get rid of that squared, you have to take the square root. So 9.9 meters per second is your answer for velocity. I have another method to solve this problem, and it doesn't require 2 steps. So I want you to look at my equation here. Instead of plugging in the 1960, I'm not going to calculate the energy at all. all I'm going to do, since I know my mgh equals my 1/2 mv squared, I'm just going to plug in my values into this equation right off the bat. This is conservation of energy. So what do you notice? If I set mgh equal to 1/2 mv squared, what do you notice about the equation that'll allow me to simplify it before I even start plugging in values? Anya? You can cancel out this mass. Because I have m on both sides, I can divide m, and I end up with gravity times height is equal to 1/2 velocity squared. From there, I can plug in my gravity of 9.8, my height of, 5, and solve for velocity from that. The calculation, notice here, is a lot faster and a lot easier than doing it from here. And what I want you to notice is I never even used my mass value. This mass of 40 kilograms, I didn't even need to plug it in because it cancels out. And when I multiply everything together, basically I can multiply 2 from both sides to cancel this out. You can do the math on your own, but if you take the square root, you end up with 9.9 meters per second in the end anyway. So it comes out to the same answer. So in this problem, we're using the exact same method. We're given a height and we're solving for velocity. So now our mgh, I'm going to write it out again. mgh is equal to 1/2 mass times velocity squared. This student figured out that calculation to be 980 joules. Because 980 joules is our gravitational potential energy, we need to figure out, if we're trying to solve for velocity, what is left over? Because our total energy, this 1960 is equal to GPE plus kinetic energy. And then from here, you can calculate your kinetic energy. So this student took the total, subtracted the 980, this one was 980, to both sides, got a kinetic energy, got a kinetic energy of 980, so it actually turned out to be balanced, and then plugged it into the kinetic energy equation, 1/2 mv squared. So then once you get your 1/2 mv squared, you plug in your values, you divide 20 like we did last class, or last problem, and then you get the square root of 49, which gives you a nice value of 7 meters per second. So for this problem, we had to solve for our kinetic energy, meaning that our LOL chart for this one was half gravitational and half kinetic. You can't make that assumption that it's half and half. You want to make sure to do your calculation to see what the ratio would be for this one. It just turned out, coincidentally, to be half and half. So this is your final answer. This worksheet right here, we're not actually going to do the whole thing. You're only going to do problems 1 through 4 today. And if you look at these problems, you've got some scenarios with springs, some scenarios with ramps, and it's a different energy transfer for every single scenario. So only do numbers 1 through 4. And what I encourage you to do is once you figure out what energy is being transferred, you are going to use this method of writing out the equation for each energy type. I want you to pull out your worksheet. Just do this LOL chart here. Don't forget to fill in the system. What's my initial energy type? Can I get a new volunteer? Danny? Kinetic energy. If you see the motion lines, there is kinetic energy. Another hint. It gives you a velocity, which means that there's speed. The next one, what do I have? Spencer.
Thermal, because it doesn't say it's a frictionless part, so there is some friction.
So I'm going to tell you that unless it tells you there's friction, assume no friction. And when we're doing solving problems like this, we're always going to kind of make it an ideal situation. Take
So I said there's elastic and thermal.
elastic, and there's a collision, which we would normally include as thermal, but in the same scenario, I'm going to say assume thermal is negligible. The reason why I'm telling you this is because we want to focus on mechanical energy. So thermal is negligible. And mechanical energy, as I stated before, is only energy that we can calculate. And if we can't calculate thermal, then we won't be able to calculate this equation, right? So let's go ahead and plug in our values. 1/2 mv squared for kinetic energy equals 1/2 k delta x squared. The reason why I am using this equation instead of the force equation for elastic energy is because I'm given K. So that's your hint to use the elastic energy equation. All right. One thing I forgot to put was my system. So there are two energy types here. That means you want to include in your system the two things that give you kinetic energy and elastic energy. What would they be? What's giving me kinetic energy? Anya. The cart. What's giving me the elastic potential energy? Julia. The spring. Some students included earth. That's fine, but there's no height change here. I had a student that included gravitational energy but kept it the same. That's correct, but it's going to make your equation a little bit harder to calculate. So I would just say limit it to one energy type to start and one energy type to finish. So we'll simplify our LOL charts to just one energy type, and it has to be a mechanical energy. Questions? Oh, one more thing. I can simplify this equation. What can I cancel out here on both sides? What am I able to cancel out on both sides? Just like what I did in the warm-up. Greta. I can cancel out this 1/2 with this 1/2. If you just divide 1/2 to both sides, it cancels out. And then you end up with a much simpler equation. mv squared equals k delta x squared. And you have all the values you need to solve for your compression distance. All right, get in your groups. You're doing the first 3 problems. And then, like I said, I want you to calculate the initial energy for number 4. You don't have to finish it. We still need to learn about work and power, so just do the initial energy for number 4, and then we're done. Once everyone's ready, you can actually pull out a red pen. We'll do the corrections in class, so you don't have to worry about it. We're going to finish 4, 5, and, just 4 and 5. Next class, because you still need to learn about work and power. I know some of you did the reading. I messed up with the homework. The homework for the reading notes are actually assigned today and due next class, but if you did it early, you got a little introduction into work and power. And homework 5-6 is conceptual questions about work and power. So let's go ahead and just do energy conversions or energy transfer calculations. For question number 1, I started it for you, and group 1 finished it. They plugged in their mass and their velocity squared, and they set it equal to 100. Hold on. Is this the K value?
Yes.
Okay, so
That's what I was saying.
Yeah. So this K value, 50, they went ahead and divided it to the other side and ended up getting 2 meters for their answer. Okay, so the next problem, we've got energy transfer from a gravitational height to motion at the bottom of the hill. The energy transfer goes from mgh to 1/2 mv squared. And this is one where you can cancel out your mass, and you end up with an equation of gravity times height, positive 9.8 times 5, equals 1/2 velocity squared. And if you multiply 2 to both sides, you get 98. Take the square root, and you get 9.9. This is very similar to what we did in our warm-up. Any questions on problem number 2? We've got gravitational to kinetic energy, and we're solving for velocity. The last problem, at least for the front page, is a spring that shoots a block up. So we've got elastic energy to start and all gravitational to end. Remember, we want these equations to start with one energy type and end with one energy type. So if some students included some gravitational energy, it's not that that's wrong. It's just going to make our equation more complicated. So we're going to say gravitational energy is negligible. So we've got 1/2 k delta x. We forgot a squared, although it was in the equation, equals mass times gravity times height. Nothing cancels out here, but you do have all the information you need to solve for height. So you end up with 1/2 times 100 times 0.3 squared to get 4.5. Half of 9.8 is 4.9. Divide the 4.9 over and you get 0.9 meters. Some students rounded it to 0.92 meters, and that's fine as well. As I stated, at least for the quizzes, I don't really grade about Docu for rounding. Now this last problem had a bullet moving at high speed. So all you could do for this problem was calculate the kinetic energy. One, the mass is a tiny bullet, so it's really small. You need to convert that mass from grams to kilograms, so 0.025. And then the velocity is really high, and you have to square that velocity. So that's 350 squared. When you take 1/2 mass times velocity squared, you get 1,531.25 joules for your kinetic energy. Now, this bullet, at the end of its trajectory, is hit by a block, and that block actually does work to stop the bullet, because in the end, the bullet's not moving. It didn't have a change in height. There's no elasticity in that block. So if you start with all kinetic energy, let's say your system was the bullet and the earth, your bullet doesn't have any more energy in it. So we call this energy coming out of the system due to the block. So the block has taken all of the kinetic energy and it transformed it into what do you think? What kind of energy do you think it transformed it into?
Thermal.
Thermal energy. It's a collision. So in this scenario, we have work being done. Here's our new equation. Work is either energy transferred in or energy out. And in this case, the block pulled energy out of that bullet. And it turned into thermal energy. Work is energy. So whatever you got for kinetic energy, this is going to be equal to your work. Vincent.
I got 0.031 meters. Is that correct?
0.0.
Oh, no, sorry for the.
No, I got the same one.
Yeah, you
Oh, did you solve it?
Yeah.
Okay, so before you actually start solving it, you need to have the equation for work. Work, like the definition of work, is when you're actually exerting some sort of force times distance. And this block obviously exerted a force on the bullet, and the bullet was able to stop in a certain amount of distance, right? So it's the same as me with this box of calculators. I'm going to try to see if my camera and you guys can see it. If I apply force to it and I push it a distance, am I doing work? I'm exerting energy. My body is doing work. It's chemical energy converted to motion. Now, what if I were to push this table? I'm exerting a huge amount of force. My muscles hurt. I'm going to start sweating in a second. Like, this is a lot of work. Is it? Am I doing any work to this table?
No,
Why not?
because you're not moving at any distance.
It has to be not just a force exerted, but a distance also. So remember how we did some concept builders, and I talked about a weightlifter lifting weights. Is that work?
Yes.
It's force exerted over a distance. Let's say instead of a weightlifter, I'm a server. I'm applying a force on this tray. Actually, was a server for a very long time in college. So we had these really heavy trays, and we had to lift them up. And as we walk around the restaurant, delivering people's food and drink, would I be exerting any, or would I be doing any work
No.
as I walk left and right? Why not?
Because there's no chance.
What do you think, Alec?
Yes, because you're moving forward.
So I've got a distance. My force is exerted upward. So this is the thing about work. If you're exerting a force in one direction, you're only doing work if your force and the distance that it's traveling in are in the same direction. So like a weightlifter, I'm doing work. Now, if I move left and right, my force is perpendicular to the direction the tray is going in. There's no change in energy because gravitational potential energy stays the same. There's some kinetic energy, but it's not due to my hand. It's not due to the force of my hand. So in this case, work is only done if force and distance are parallel to each other. If the force you exert actually moves an object in that same direction or parallel to that direction. Out.
Isn't like the force from your legs moving?
So that would be different. If I were talking about my body's moving left and right, my legs are pushing it left and right, so that would be my legs doing work on my body. But my hand, in reference to the tray, not work. So keep in mind they have to be parallel to each other. There has to be movement, so you can't have work done without any actual change happening, right? So this is work. The other thing we're going to talk about is power. Power is the rate in which work is done. So it's work over time. So if I lift this weight really slow versus really fast, power is related to your productivity. How fast can you do something? We're doing the same amount of work, but one person's doing it faster, which means they exert more power. Next class, we're actually going to be doing a work and power activity. So we're going to be outside on the bleachers. You're going to be doing some exercising. Wear comfortable shoes. Wear warm clothes just in case it's not sunny. Come here to class first, but be prepared to be outside next class.